Welcome to Learning Unit 5B, which is about failure in materials. Materials fail through the growth of cracks in the material. And a crack or a fracture is a separation of a body into two or more pieces in response to an imposed stress that is static or slowly changing with time, and at temperatures that are low relative to the melting temperature of the material. Under such a definition, the causes of fracture are overstress, which is applying a load that exceeds the tensile strength of the material; fatigue, which is the initiation and growth of cracks under loads that are below the yield stress, but these loads are cyclical in nature and they cause the growth of cracks in the material. Creep is a time-dependent strain in the material that occurs at elevated temperatures, and corrosion is chemical attack of the material from the environment in which it is operated or used. So we will consider these four types of or four causes of fracture in this module. There's a discipline in material science called fracture mechanics, which is concerned with the study of materials containing cracks. Excuse me. There is a discipline in material science called fracture mechanics. Fracture mechanics is concerned with the study of material containing cracks or flaws, and all manufactured materials will contain some voids, cracks or flaws. The purpose of fracture mechanics is to study how these cracks grow, and that information or that knowledge can be used to determine if a material containing a crack or flaw will be suitable for a certain application. The fracture of material can be classified into three main types: a highly ductile fracture, which is characterized by a high amount of elongation of the material before it ruptures. A moderately ductile fracture is one when there is some yielding and plastic deformation and then cracking. And the brittle fracture is a fracture in the material in which there is virtually no ductility and there is no plastic deformation in the material before it cracks. In a ductile feature, we see a classic development of a neck in the material as the material deforms under shear forces, and the formation of a characteristic cup and cone. So we see there's a better picture of a cup and cone here. This would be the cup and this would be the cone. In order to understand how this classic fracture is formed, let's have a look at this diagram. We see that under loading we see the creation of microvoids. These microvoids coalesce or come together to form a larger crack, and eventually what happens is there's not sufficient cross-sectional area to support the load, and we get cracking or fracture of the material. But at the edges here we see shear failure, and hence the sloped cup and cone feature. If we look at the microstructure of the material, at the center of the sample we will see equiaxed, meaning of equal dimension in all axes, equiaxed voids. On the sides we will see the voids become stretched into ovals due to the shearing of the material. So we can use this kind of knowledge to perhaps form, to do analysis of failures, for instance, and to determine what kind of failure mode occurred. Here we see a brittle fracture. Here we see a brittle fracture, and we can see there is very little plastic deformation of the material. If we put the two pieces together, they would still fit very closely. Brittle fractures are characterized by a chevron propagation shape, and where the chevron rays focus, that would be where the crack was initiated, either by a flaw there or an impact. Glasses have, or amorphous materials, have a very characteristic crack shape, and it's called conchoidal or conchoidal because these are reminiscent of the lines on a conch shell. This is an example of a very large conchoidal fracture. In polycrystalline materials, the fracture can be transgranular, meaning the crack goes through the grains, which will result in a smooth fracture surface. And here we see a smooth fracture surface from a transgranular fracture. I should have put the scale on there. An intergranular fracture is when the fracture propagates along or between the grains. This is where this could occur if there is a second phase, a weaker phase, or a more brittle phase present at the grain boundaries, or another reason for weakening at the grain boundaries. In an intergranular fracture, the fracture surface is more faceted as it follows the contours of the grains. We're now going to consider some mathematical approaches, or just some simple mathematical equations for determining the effect of flaws. So in this case we see a pressure vessel, and inside the material we could say that there exists a flaw of a certain dimension. Here the dimension 2a is given. And what does that flaw do? Here we see two images of a piece of glass, and the stress inside the glass has been calculated. If the glass doesn't contain any flaws, the stress is uniform and low. If the glass has a flaw in it, here a crack has been introduced and the analysis has been repeated, and you can see that at the tip of the crack a very high stress is created. Cracks act as stress concentrators, and this very high stress the very high stress is created at the tip of the crack, cause that crack to rip through the material or propagate. What we'd like to do is to figure out at what stress will a crack of a particular size propagate. The stress intensity factor is a mathematical construct from the theoretical approach of looking at how stresses increase due to the presence of a crack, basically, with a very sharp radius. Under such conditions, the stress at the tip becomes what is a singularity. It becomes very high, and there's mathematical approaches have been taken to describe the stress distribution in such cases, and this number, the stress intensity factor, has found a useful parameter. The stress intensity factor K is equal to F, which is a constant dependent upon the geometry for the specimen and the floor. Sigma is the applied stress. A is the floor size, which will be as defined on the diagram I'm about to show you next, and this is pi. So according to this theory, we must use the following values for A to describe the crack. So for a surface crack, A is the depth of the crack, and typically F will equal 1.12 for a surface crack of depth A. For a crack inside the material, an internal crack of width 2A, the F will equal 1. So this is how we determine the A values and the F values for different locations of the crack. Now, it has been found that when a stress is applied such that the value of K reaches a certain value called the critical fracture toughness, or the critical stress intensity value, which is known as the fracture toughness, when the conditions are reached where the fracture toughness reaches the value, or where the stress intensity factor reaches the value of the fracture toughness, the material will crack. So the floor will open up into a crack under such conditions. So if we know the fracture toughness of the material, we can work backwards and determine what stress can be applied to a material safely if we know the size and shape and location of the cracks. So that is the usefulness of the fracture toughness. The higher the fracture toughness, the more tough the material. And as we defined in the last chapter, toughness is the ability of a material to absorb impact energy. The following factors influence fracture toughness. The ductility of a material. Ductile materials blunt crack growth and are hence tough. The thickness of the specimen. The fracture toughness decreases with the thickness of the specimen. After a certain point, it reaches a constant value, and that constant value is known as the plane strain fracture toughness. Increasing the strain rate, so under, say, impact loads, that decreases fracture toughness. Increasing temperature increases fracture toughness, and smaller grain sizes impede crack growth in a specimen. Here we see some samples that could be used for fracture toughness measurements. You see that a notch of a well-specified geometry is cut into a specimen, and then the specimen is loaded at the lobes. So I'll just use my pen here. Is loaded at these lobes, and here we go. So if the sample is pulled like so, we create a very high stress concentration right here, and at a certain point a crack will propagate in the material, and we can calculate the fracture toughness from that. This is a smaller sample and smaller still. We see here how the fracture toughness, K sub C, reduces with increasing thickness of the specimen until we reach a low value. Okay, and this low value is the plane strain fracture toughness. Now I'll just underline that for you. Right here, the plane strain fracture toughness. Fracture toughness may also be applied using a diamond indenter on microscopic specimens, and we can determine the cracks, the force that is required to cause cracking in the material at the edges of the pyramid-shaped indenter. Here we see some data for yield strength and fracture toughness. We see, for instance, alloy steel has a very high fracture toughness. Ceramics have a very low fracture toughness, and polymers, the fracture toughness of polymers varies depending upon the type of plastic. Fracture toughness is also dependent upon temperature. Here actually we're looking at the toughness, the impact energy versus temperature. This is for steels with different concentrations of carbon. We see that increasing the concentration of carbon from 0.01 to 0.067 makes the material harder. Harder materials are less tough because they are brittle. Low alloy steels are ductile and hence tough. However, at low enough temperatures they will undergo a transition into a brittle material. And in fact, all of these show a reduction in toughness with lowering of temperature. So materials will become brittle at lower temperatures, and it is important to keep that in mind when designing for low temperature use. It is believed that the composition of the steels used in the construction of the Titanic was such that their brittle or their ductile to brittle transition was around the -2 degrees centigrade region. So the Titanic, being in icy waters, would have been in such a state that the material would have been brittle and would not have been able to absorb the impact with an iceberg. So what can we do with this fracture toughness number? We can use it to select a material for a particular application and allow design the component to meet the service load conditions. And if we can determine what the size of the flaw is, or that will still be safe in the material, we can then suggest testing techniques that will ensure whether the device is or the structure component is safe or not. I'm going to do an example to try and explain how we apply fracture toughness to some simple design cases or textbook problems. A structural component in the form of a wide plate is to be fabricated from a steel alloy that has a plane strain fracture toughness of 77 megapascals. So this value is the KIC value, the plane strain fracture toughness. Okay, I'm not sure why it won't let me write C, but there we go. There we go. And a yield strength of 14 megapascals. The floor size resolution limit of the floor detection apparatus is 4 millimeters. If the design stress is 1/2 of the yield strength and the value of Y is 1, determine whether a critical flaw for this plate is subject to detection. Okay, so let's have a look at we're going to apply the fracture toughness equation. Which is that K is equal to F sigma square root of pi a. So we know that the fracture toughness, Kc, is equal to F sigma and the square root of pi times A. In this case, we know the value of Kc. It's equal to 77 megapascals. So we know that. Now, we want to determine whether under a load, it says that sigma is, in this case, equal to half sigma y, the yield strength, which is half multiplied by 140 megapascals. It doesn't really matter whether you use the SI units or the American customary units. You just make sure you're consistent. So we've got 1400 megapascals. So we want to know what size of floor, what's the maximum size of floor that is allowable in the material with a fracture toughness of 77 megapascals and under a load of 700 megapascals, or under a stress of 700 megapascals. Let me just make sure that 7 is easier to read. So what we're going to do now, we want to solve for A for different situations. For both surface and internal floors. So we know that actually they tell us here that the value of y, which is also used in the book as f, okay, in this textbook, f and y are used interchangeably. So we're going to use, here the sensible thing to do is to use f equals 1 for both. A surface floor of depth A and an internal floor of size 2A. Okay, so first of all, what we can do, we can rearrange equation 1 to find A. So what do we get? Kc squared divided by f squared sigma squared divided by pi is equal to A. So I just squared both sides and I rearranged for A. In such case, we can plug in the numbers. (77 times 10 to the 6) divided by F, which in this case is equal to 1, sigma, which is 700, so let's calculate this out. KC is 77, so 77 times 10 to the 6 squared divided by F squared, which is 1 squared. Sigma is, this is the applied stress, 700 times 10 to the 6, and we want to square that and multiply by pi. And when we work that out, I get 3.85 millimeters. So this tells us that if I have a floor at the surface of 3.85 millimeters, then if I have a floor that's greater than 3.85, then the material will crack because we've exceeded the stress intensity factor. What I'm trying to say is the stress intensity factor for if the crack is greater than 3.85 will be larger than the fracture toughness, and the material will crack. In this case, in the case of an internal crack, then the internal floor can be 3.85 times 2, which is 7.7 millimeters wide. So what can we say from this? We can say that, if I just use the detection method can find a floor. The resolution limit of the floor detection apparatus is 4 millimeters. That means that the smallest crack it can find is 4 millimeters. That means our crack detection cannot detect a 3.85 millimeter crack, and so it cannot detect a surface crack that could cause failure of the material. However, assuming it works equally well for internal floors, it can detect any floors that are bigger than 7.7. So an internal floor of 7.7 will cause cracking. If it's smaller than that, will be okay. So our detection method will work for internal floors, but for floors at the surface, it's not good enough to detect cracks smaller than between 3.85 to 4. So we have to find another method to test these samples to ensure that they will work in operation or in service. So that brings us to the topic of different types of flaw detection methods. These are called non-destructive testing. Non-destructive testing is the ability to test a component without destroying it. And of course, this is one way to test a batch of samples is to take a few of the samples from the batch and then test them to breaking point. This is of course expensive and is not always reliable. For instance, we may have just picked 2 good samples out of the batch. Non-destructive testing allows us to test the actual component that will be used in operation, and if it is not economically feasible to make more than one for testing, then non-destructive testing is the way to go. So there are different techniques here. We've got scanning electron microscopy. This is a very sensitive technique, but it can only be used for relatively small samples that will fit into the microscope. Dye penetrant, that is a technique that relies on spraying the surface of a material with a dye that penetrates into the cracks. We then wipe off the excess and then use a UV light to detect where the dye was trapped. We can use ultrasonic detection to find subsurface cracks up to 0.05 millimeters. Optical microscopy can be used, but obviously very difficult to do large areas. Visual inspection, works greater than 0.1 of a millimeter. Acoustic emission and X-ray radiography can work for in certain cases. The next thing I want to talk about is fatigue. Fatigue is a failure of materials under repetitive loads, and these repetitive loads are often well below the yield strength of the material. What do we mean by cyclical loading? Cyclical loading is a loading pattern that repeats itself in time. Here we have a sinusoidal cyclical loading, and here's the 0 line. This is a general case of cyclical loading. Cyclical loading can vary about a mean value, so this is the mean stress value that is either positive or negative. And then about that mean we have a variation. The amplitude of that variation is the distance indicated by this arrow. We also have another parameter called sigma min or minus sigma max or vice versa. We're just looking at the size of that, and this is the mean value, sigma mean. And here's the maximum value. We're going to look at a very simple loading which has 0 mean but varies about 0 mean with a certain amplitude. What happens under cyclical loading is that a crack will nucleate at a defect or a region of high stress. Perhaps there's a notch or deliberately cut into it that has caused a stress concentration. The crack nucleates at that point, and then with repeated cycling the crack grows, and then the component eventually fails when the cross section is too small. This is shown schematically here, where we have the initiation, the growth of the crack after each cycle, and then finally catastrophic failure when the remaining area is not sufficient to support the load. How do we do fatigue testing in the lab? We do that by having offset bearings. So we're twisting the sample, but the bearings are offset. so the surface of the sample undergoes compression and tension every time it is rotated. We have a motor that rotates it and a counter, and we count the number of rotations to failure. If you watch the video on the link, you can actually see the test in action. This is also a great video showing a Boeing 787 fuselage being fatigue testing, where they repeatedly pressurize it and depressurize it, simulating what happens every time it takes off and lands. When we do the lab tests, we can plot a curve called a Wöhler curve. The Wöhler curve plots applied stress against the number of cycles on a logarithmic scale. So what we see is that the number of cycles to failure increases as the applied stress decreases. In the case of a tool steel, the curve flattens out, and so if we have a stress that is below this level, then it should last forever, for an infinite number of cycles. And this limit is called the endurance limit. The endurance limit. So we can see the arrow should have pointed there. Endurance limit is 60,000 psi. Let's have a look at aluminum. We see aluminum, just the number of cycles to failure keeps basically there's no plateau here. That tells you that there's no endurance limit for aluminum alloys. That means anything made out of aluminum has a finite life. It doesn't matter how low the stress conditions are. And this has importance for aircraft, for instance. If you think the vibrations that the skin of the aircraft, the wings and the structure of the aircraft is susceptible to, and also what happens to the fuselage every time it is pressurized and depressurized. So the life of aircraft is actually not measured in hours, but measured in terms of the number of pressurization, depressurization cycles. Because the failure mode of the material, of the aluminum material that is used, or is still widely used for aircraft skins, is aluminum, or an aluminum alloy. Here we see an optical micrograph of a fracture of a shaft, and we see that a keyway cut into the shaft to allow it to basically bond to some other rotating object has resulted in a sharp corner that has initiated a crack, and with each rotation the crack has grown until final rupture. If we look at the crack growth propagation region under a microscope, we see these fine beach marks that indicate a fatigue fracture. So we can see here another shaft. We have a region of slow crack propagation under fatigue, and then finally it gets so small the whole thing cracks, and then you get a region of rapid crack failure. I would really encourage you to watch this video. It's about one of the first commercial jetliners built by de Havilland in the 1950s. It became a great commercial success, but then there were a series of accidents, mysterious accidents. The planes were falling out of the sky, and intensive tests were done, and it was realized then that the fuselage was failing due to fatigue, due to a particular design flaw and installation flaw with the windows. And it was one of the first cases where the fatigue wasn't very well understood then, but it was one of the cases that really highlighted the importance of fatigue in design of aircraft. And actually, because as a result of those accidents, the de Havilland company lost market share, and as a result, they say Boeing became the leading manufacturer of jet civilian aircraft. So how do we prevent fatigue failure? If the material has an endurance limit, then we can reduce the stress amplitude below that level. We can also help by avoiding stress concentrations due to sharp corners. And we can also process material to create a compressive residual stress at the surface, which will close up any cracks. So this is an example how the shape of the shaft can increase the resistance against fatigue. In shaft A, we have a very sharp transition in terms of the cross-sectional diameter of the shaft. This leads to a stress concentration. It's much better to have a rounded transition or a fillet. So the fillet region is right here. And this will result in an increased lifespan for the component. There is a process called shot peening, where you bombard a component with metal shot. And what this does, this creates compressive residual forces at the surface. And the compression or squashing of the material at the surface prevents cracks from propagating, from opening up basically and passing through the material. So shot peening increases the cycles to for a given stress amplitude, it increases the cycles to failure. So it makes it fatigue resistant. Here we see a micrograph study of case hardening. So this could be nitriding or carburizing. The nature of the process both hardens the material, as can be seen by these indentation marks. The indenter makes a larger indent in the softer region than in the harder region. In the harder region also, in the hardened region, there is a compressive stress, which is basically this material is in compression due to the processing and prevents cracks from passing through the surface. The next thing I want to talk about is creep. So creep is a time-dependent strain under a constant stress, and it particularly occurs at high temperatures. And diffusion and grain boundary sliding are important mechanisms for creeping metals. If we have a look at the creep strain versus time, we get a graph like this. In the middle, it looks linear, and we can specify a creep rate, which will be the rate of change of strain with time. Creep rate can be given by this equation, this Arrhenius relationship, which are typical for thermally activated phenomena. And we see here C and N are constants for the material. Sigma is the applied stress. Q is the activation energy per mole for creep. If we do creep tests at different temperatures, we can plot a graph showing the stress applied and the time that is to rupture for a component at different temperatures. We see that as for a given stress, let's say 2000, we see how increasing the temperature leads to a lower lifetime, basically. The rupture life is the time for which the component will last. There's a way to plot all of this information on one graph, and that's by converting the temperature, or combining the temperature and time, into what is known as a Larsen-Miller parameter. What we're doing, we're plotting the stress being applied versus the Larsen-Miller parameter, which combines temperature in Kelvin and T in hours. A and B are constants determined for the material from tests such as these. Let's practice applying the concepts of the Larsen-Miller parameter to this simple problem here. It says a 1" by 2" ductile cast iron bar must operate for 9 years at 650 degrees centigrade. What is the maximum load that can be applied? See the figure 727b, so I've reproduced it here. So the way to solve this problem is we have stress versus Larsen-Miller parameter for the specimen. Constants A and B have been determined for us. We need to determine what the Larsen-Miller parameter is for the temperature and time, and then look up what the maximum stress is and multiply that by the cross-sectional area to get the maximum load. Okay, so let's see how to do that. First, for the environmental, for the time and temperature, the Larsen-Miller parameter is 650 plus 273, that's Kelvin. Divide that by 1,000. Multiply that by the constants given in the definition for the equation for the Larsen-Miller parameter for this material, plus 0.78 ln T's in hours. We need to convert 9 years to hours. 9 times 365 times 24. So let's calculate this out. And I got 41. So if we go to our graph now, we see 41 is about there, and 41.3 is about here. So I should double check my calculations. It looks a little bit high and not on this graph. But let's extrapolate the graph, and assuming this is correct, we can read off now the maximum stress, which is 1000 psi. So we can say here, therefore, the maximum stress allowed under these operating conditions is 1000 psi to ensure a lifetime of 10 years under the loading, to account for the degradation due to creep. So we can now calculate what the load will be, because we know that sigma is force over area. Therefore, the load, the force, is going to equal 100 psi, 100 pounds per square inch, multiplied by the area, 2 inches by 1 inch. So that's 2 square inches, and that gives us a number of 2,000 pounds for the maximum load. We talked about the mechanisms of creep. We talked about diffusion, grain boundary sliding. Here we see an example of the development of jet turbine blades, and how which are severely affected by creep due to the high temperatures and loads that occur within the engine. So in an effort to increase the lifespan of the blades, by applying the theory of creep, the technology has gone towards making single crystal turbine blades. The reason is that a polycrystalline blade has a lot of grain boundaries, and it's the sliding of grain boundaries that is giving rise to one mechanism of creep. So one way to get rid of that easy mechanism is to get rid of the grain boundaries. So the next step is to do that by the technology advanced one step further to make columnar grains. That helps, and then it advanced even more to make a single crystal turbine blade. So there are no grain boundaries in it, which means there are no grain boundaries that can slide over one another, thus increasing the creep resistance of the blade.